In this video, you will learn how to write expressions for equilibrium constants and calculate their values and units. Consider this chemical reaction at equilibrium. It is found experimentally that the equilibrium constant can be expressed as being equal to the concentration of C multiplied by the concentration of D divided by the concentration of A multiplied by the concentration of B. Each concentration in turn raised to the power of their respective stoichiometric coefficient in the balanced chemical equation. The brackets around each substance denotes that their equilibrium concentration is measured in units of moles per dm cube. And what we have obtained is the equilibrium constant expressed in terms of concentrations. We will now derive the equilibrium constant expression for the reversible reaction between nitrogen and hydrogen to form ammonia. The equilibrium constant is equal to the concentration of ammonia divided by the concentration of hydrogen multiplied by the concentration of nitrogen. The concentration of ammonia is raised to the power of 2 and the concentration of hydrogen is raised to the power of 3. This corresponds with their respective stoichiometric coefficients within the balanced chemical equation. Next, we will determine the units for the equilibrium constant in this expression. Remember, each substance in brackets represents the concentration in moles per dm cube. Therefore, we have for the numerator mole per dm cube raised to the power of 2, and for the denominator mole per dm cube multiplied by mole per dm cube raised to the power of 3. Simplifying, we obtain the units of this equilibrium constant. Take a moment to think about what you have just observed. Because the units of the equilibrium constant depend on the form of the equilibrium expression, the units of Kc may vary from one reversible reaction to another. It is also possible that the equilibrium constant does not have units for some reversible reactions. Now you are going to write the equilibrium constant and its units for this reaction. Pause the video and resume only when you are done. Let's check your answers. Here is the next reaction for you to try. Again, pause the video and resume only when you are done. Let's check your answers. For reactions involving mixtures of gases, it is easier to measure the pressure than to measure concentration. We write equilibrium constant expressions in terms of partial pressure in a similar manner to that of in concentrations. The differences are, we use the symbol Kp instead of Kc. We use the symbol P for partial pressure, with the reactants and products written as subscripts. Each partial pressure is raised to the power of their respective stoichiometric coefficient used in the balanced chemical equation. Square brackets must not be used, and the units of pressure are either pascals or atmospheres. What we have obtained is the equilibrium constant expressed in terms of partial pressure. Next, we explain what is partial pressure. The total pressure in a mixture of gases is due to each molecule bombarding the walls of the container. At constant temperature, each gas in the mixture contributes to the total pressure in proportion to the number of moles present. The pressure exerted by any one gas in the mixture is called its partial pressure. The value of partial pressure for each gas can be obtained by multiplying its mole fraction with the total pressure. We will now derive the expression for Kp of this reaction and its units. It's equal to the partial pressure of hydrogen iodide raised to the power of 2 divided by the partial pressure of hydrogen multiplied by the partial pressure of iodine. Brackets are used here to make identifying each partial pressure easier. This is not compulsory. However, square brackets must not be used, and you will be deemed incorrect if you do so. Next, we determine the units. If partial pressure is measured in atmospheres, then for the numerator, we have atmospheres raised to the power of 2, and for the denominator, we have atmosphere multiplied by atmosphere. Simplifying, we obtain that there are no units for this value of Kp. Now, write the equilibrium constant expressions in both concentrations and partial pressure for this reaction along with their respective units. Pause the video and resume only when you are done. Let's check your answers. Next, you are asked to calculate the value of Kc. To do this, examine the information given. Think about how they can be linked to the Kc expression. Pause the video and resume only when you are done. To obtain the value of Kc, we substitute the concentrations of the reactants and products at equilibrium into the equilibrium constant expression. Now, find the value of Kp. Remember, the partial pressure of a gas can be obtained by multiplying its mole fraction with the total pressure. Again, pause the video and resume only when you are done. To obtain the value of Kp, we will need the partial pressures of the reactants and products at equilibrium. The respective partial pressures can be obtained by multiplying their mole fraction with the total pressure. We then substitute them into the equilibrium constant expression. Take note that in reversible reactions where the reactants and products exist in more than one phase, the concentrations of pure liquids and pure solids will not appear in the equilibrium constant expression. In this reaction, zinc metal displaces copper 2+ ions from solution. Because there are no gases, it is not possible to have an equilibrium constant expression in terms of partial pressure. For Kc, we exclude the concentration of solid zinc and copper and only have the concentration of zinc 2+ ions divided by the concentration of copper 2+ ions. When ethanoic acid is dissolved in water, it produces an acidic solution. the Kc expression for this reversible reaction does not include the concentration of water. This is because water is acting as a solvent and its concentration remains essentially constant. In this final example, the concentration of both solid phosphorus and liquid phosphorus trichloride do not appear in either of the Kc or Kp expression of this reversible reaction. This is the last exercise. Pause the video and resume only when you are done. Let's check your answers. Since we do not include the concentration of solids in the equilibrium constant expressions, Kp is therefore equal to the partial pressure of carbon dioxide only, and its value and unit is 0.230 atmosphere. Kc is also equal to just only the concentration of carbon dioxide in moles per dm cubed. To obtain this value, we can make use of the ideal gas equation. By rearranging the equation, we are able to relate the concentration of a gas in moles per dm cubed to its partial pressure in atmospheres. Substitute in 0.230 atmospheres and convert it to pascals since it's the units used in the ideal gas equation. Divide this by the molar gas constant and the temperature at 750 degrees Celsius converted to Kelvin. You will then get your answer. You should now be able to write equilibrium constant expressions and determine their values and units. After this video ends, you should find out more, like why a particular value of Kc or Kp is constant for a given temperature, and the significance of its numerical value.